Good evening to all. Myself, Dr. A. Sudhakar, working as Professor, Electrical and Electronics Engineering Department, Gates Institute of Technology, Gutti, Andhra Pradesh, India. So today's topic is reduction of torque ripples using the direct torque control space vector modulation method in permanent magnet synchronous motor with extended Kalman filter. My paper ID is 21337. So coming to the presentation, so the abstract of the paper is, so the permanent magnet synchronous motor speed can be controlled by various speed control methods like direct torque control method and field oriented control methods. So in these different speed control methods, so the voltage source inverter will be providing the variable voltage in order to control the speed of the motor. So the selection of proper voltage space vector plays a very key role in the adjustment of the voltage provided by the voltage source inverter, through which the speed of the permanent magnet synchronous motor can be controlled. So here, if at all the voltage vector is not properly selected, then it will be resulting in various disadvantages like torque ripple and flux ripple, and thereby reducing the performance of the motor, and we cannot get a precise control on the speed of the synchronous motor. So here, if by using a extended Kalman filter, which is a stochastic probability method through which we can select a proper voltage vector, due to which we can apply the relevant voltage in getting the speed control of the permanent magnet synchronous motor. So coming to the introduction part, as we know that the synchronous motors are having a wide range of applications in different industries and home appliances. So the different application of different speed control methods like the DTC, field-oriented control methods. Okay, we will be observing so many disadvantages like torque ripple, flux ripple. So they can be reduced by using optimized methods like extended Kalman filter, etc. So here, if we observe the basic block diagram of direct torque control space vector modulation control technique. So the output of the permanent magnet synchronous motor, okay, so is monitored. The different stator currents like IA, IAS, IBS, ICS are sampled, and the rotor position theta is also sampled continuously and given to the motor model as input. So this motor model will be providing the stator flux, the stator position, then DQ components of the flux and rotor position as input to the DTC space vector modulation controller. So the DTC space vector modulation will be continuously getting inputs from the stator flux and the torque error. So if we observe, we are using a PI controller in order to continuously monitor the error between the estimated torque and the actual torque. So this delta del represents the error between the estimated torque and the actual torque. So which is optimized by the PI controller. So the DTC-SVM controller will be giving the voltage vector, stator voltage vector, and the position of the voltage vector, which are given as input to the space vector modulator. So the space vector modulator will be providing the state voltage vectors S1, S2, S3, which are given as input to the pulse width modulation inverter. So if we observe this particular block diagram without extended Kalman filter, so the proper selection of state voltage vectors S1, S2, S3 in the 360 degrees. So here there are 6 regions. If we don't select a proper state voltage vector S1, S2, S3, the output of the PWM inverter will not be specific and precise. Thereby, we cannot get a required amount of output voltage applied to the PMSM, which will be resulting in torque ripples, flux ripples, and thereby affecting the performance of the motor. So now if we observe the extended Kalman filter, so here for the same block diagram, we are just placing an extended Kalman filter at this particular point, where the extended Kalman filter is an iterative process which will be processing the dynamic nonlinearities in the parameters, and it will be helping to choose a proper state voltage vectors, which in turn will be providing the PWM inverter to provide the specific voltage as input to the PMSM, and thereby getting the required desired output speed. So here, if you observe as I said, that the extended Kalman filter is an iteration technique which will be estimating the dynamic and nonlinearities of the systems on least square method. So here it will be giving a accurate value in spite of so many disturbances like noise, random Gaussian, etc. So here we can apply EKF. So if we see the results of the DTC-SVM method for PMSM, so the speed of the speed graph of PMSM without Kalman filter can be observed in this figure. Then if we observe the torque parameter, so whenever there is a changeover in the load, which can be observed at 0.2, whenever we are applying a load of 30 Newton meter, there is a lot of ripple that can be observed in the torque when Kalman filter is not implemented. So even in the stator current also, we can observe that the disturbance is more in the stator current whenever the Kalman filter is not applied. So whenever the Kalman filter is applied, so a probabilistic method, iterative process where the ripple can be reduced to a large extent. So in the similar way, the flux ripple also can be reduced by the implementation of the Kalman filter. And even if we observe the stator current here, it is a lot smoother compared to the stator current pattern which we observed without Kalman filter. So in CRISP, if we observe the table of results with and without Kalman filter, so the torque ripple without Kalman filter is around 10%. So with Kalman filter, the torque ripple content has reduced to 3%. So the peak overshoot of stator current is 20 amperes without Kalman filter. And when we are using the Kalman filter, it has reduced to 7 amperes. So if we observe the stator current ripple, so without Kalman filter, it is around 2.4. And with Kalman filter, it is 0.6. So in this way, we can observe that by using a Kalman filter, there is a significant reduce in torque ripple and peak overshoot of stator current and stator current ripple. So here coming to the conclusion, so from this we can observe that in the different speed control methods like direct torque control and field oriented control, which are applied to the PMSM. So by using the EKF extended Kalman filter, we are able to reduce the torque ripple, flux ripple, and in turn, it will be improving the performance of the synchronous motor. So further, this work can be extended by using different intelligent controllers like neural and fuzzy controllers. So thank you for giving me this opportunity. Thank you.